Good morning, everyone, or good afternoon, I guess. Yeah, we're sitting in the afternoon now. Good to have you all here. So we'll get started with a little bit of housekeeping, just on what the next week is going to look like or so. So I can share screen here. Okay, so pulling up the syllabus so we can look at it together. Just a couple of things I want you guys to make note of. So Labor Day didn't affect us, so we'll have 2 opportunities for lecture this week, which is good. The chapter that we're working on right now is talking about atoms, molecules, and ions. It is going to get into this thing called nomenclature. Nomenclature is just a fancy way of saying naming. So naming chemical compounds. So you guys are going to learn how to name a bunch of inorganic compounds. For your experiment this week, you're doing a nomenclature assignment in Mastering Chemistry, okay? So that is due Sunday at midnight at 9:13. You notice your test is going to be available for you Sunday 9:13 through Monday 9:14, okay? So you figure out what's convenient for you. If you'd rather do it Sunday, if you'd rather do it Monday, whatever. That's fine, but once you get started on the exam, you have to finish the exam, okay? So you have an hour and 15 minutes to finish. I believe the first one is 42 questions, multiple choice. You can use your notes. You can use a periodic chart. You cannot take the exam with somebody else, and you can't use the internet outside of obviously submitting your answers. So just keep that in mind. If you don't complete the test by Monday, then you've missed the opportunity to take the test. So just make sure that you take it, even if you're like, oh, I don't know any of this. Still take it, right? Maybe you may surprise yourself. So that's looking forward this week. One thing I would note though, this nomenclature experiment or the Mastering Chemistry assignment, do this before you take the test, okay? This is going to be very, very good practice for all the naming stuff that will be on this test. So don't leave this Mastering Chemistry assignment for after the exam. Do it before the exam. It will be very helpful. So let's get out of the syllabus. I did add a link on the Moodle pages for lecture videos. It says it's lecture videos YouTube channel, Candace and Chemistry. So that is my YouTube channel. It should take you to this link here. Where you guys are obviously in Chem 151. So you would want to view the playlists. And then from there, you can see all the videos. I have to post last Thursday's video. My computer moves so slow, it takes so long. Thought we had to do experiment 3 this week. Don't believe that that's what's on the syllabus. Let's go to Moodle here. So experiment 3, we can see here on Moodle, this isn't due until 9:20. So we're gonna take a break, a 1-week break from submitting things here, and you'll do it in Mastering Chemistry, if that makes sense, okay? So this one isn't until next weekend. So yeah, with the YouTube channel, click on the 151 playlist and you'll see them ordered by date. I will get Thursdays and today's up, hopefully sometime today. Just takes a while for my computer to upload. Okay, cool, good, awesome, yeah. On my YouTube channel, you'll see that there are some other classes, Chem 130 and Chem 092. You don't need to look at those. Won't do you any good. All right. Let's see if there's anything else I wanted to talk about. I've had some people ask me, how do I do the labs if I don't have the information? Use this link here. This is the link to all the lab resources, videos, and instructions. So, oh, Jason, I like your background. Yeah. So use this to fill in the missing information. Like when it says, hey, what's the mass? What's this? You can't run the experiments, right? So you'll get all that information here. All right, here's where your test will be. So you've got all your tests lined up here. You'll just click on it and it'll prompt you to take the exam. Once you click on it, it starts the time for 1 hour and 15 minutes. Looks like you can complete it between Sunday at 5 a.m. And Monday at midnight. There's a little honor code here thing too that says I pledge that I've used only my notes textbook formula sheet to complete the test. So please honor that. This will not open before the designated time, just so you know. Okay, so let's go ahead and continue lecturing. And I think that's all I wanted to say about all that stuff. Yeah. All right. I'd love to see your faces, but I'm gonna close you guys up for a little bit. I'll bring you out later. You are always in my way. Okay. So last time we left off talking about isotopes. And so an isotope is an atom of the same element, but it has a different mass. How can it have a different mass? The only thing that you can change is the number of neutrons, okay? You can't change the number of protons. If you change the number of protons, you would end up with a different element. So we wouldn't then be the same material. If we change the number of electrons, that doesn't change its mass. It does change its charge, which we'll talk about a little bit later in ions, but it doesn't change its mass. So we definitely don't worry about electrons. What we do worry about when we're talking about isotopes is a shift in the number of neutrons. So carbon 11 is our lighter carbon. It will always have 6 protons. In this case, because there's no charge in the upper right-hand corner, always has 6 electrons. The thing that's different is the number of neutrons. We've got 5 here. Now you get this number in the upper left-hand corner by taking 6 plus 5 gives us that total of 11. If we look at carbon 14, which is radioactive carbon, it has a bigger nucleus. It's heavier. So it's got 6 protons still, but we have to compensate now for a difference in a mass of 3, which goes from 5 to then the 8 neutrons. This bigger nucleus with 8 neutrons packed in it is a little bit more unstable than some of these smaller ones, hence why it's radioactive carbon. You can use that for dating. So we talked about the atomic mass, or the AMU. So atoms have an extremely small mass. The heaviest known atoms have a mass of approximately 4 × 10⁻22 grams, so super teeny tiny. So when we're talking about an AMU, when I'm referencing that, saying, oh, it has an AMU of 26.2. 1 AMU is approximately equal to 1.66054 × 10⁻24 grams. We don't really use this relationship, but you just need to know that it is, in fact, 1 AMU is a very, very small amount of grams. So atomic weight. So because in the real world we have a large amount of atoms and molecules, we use average masses in our calculations. So if you've ever looked at a periodic chart, I'm going to pop forward. These periodic charts are all rounded. I don't like that. Excuse me, hold on one sec. I'm going to pull one up here. I don't want one that's rounded. It's all rounded. time. It's grounded. Oh, come on. No, this one we should be able to use. Okay. Oh, it's so crappy. Hold on 1 second. I used to have, my desktop used to be the periodic chart, and I don't know where it went. Nice. Fair enough. Oh, doesn't like that. Okay, okay. Oh no. You don't want that. Sorry guys, this is one of those things that you don't think about when you have to teach online and you think, where is my periodic chart? That's usually like right behind me on the wall, and now I don't have one. I mean, I have one on my textbook, but I don't have one that we can all look at together that doesn't have the numbers grounded, which is driving me crazy because it looks like, yeah, they don't have the atomic masses on it. Come on. Just want one that we can read. No. Okay, there. Oh, it doesn't even have them on there. Come on. Okay, there we can click on the atomic mass in there. Okay, so looking at this periodic chart, it doesn't have the atomic mass specifically on there, but if I go to, let's go to one that's, let's go to hydrogen first. Okay, so hydrogen has an atomic mass of 1.0080. So when we're talking about atomic mass is the number of protons plus the number of neutrons. So you would think that that number should be a whole number, right? Because you can't have partial protons, you can't have partial neutrons. Threat detected. Oh no, I'll have to deal with that later. So you can't have partial protons and partial neutrons. So why do we have this decimal place? Another one where we can see this happening is chlorine, for instance. Yeah, I hear you. Chlorine has an atomic mass of 35.45. So again, you know, we would want that number to be like 35 or 36. Why is it 35.45? Well, how is there a decimal if we can't have half protons and half neutrons? Well, the reason that we have a number that's decimaled is because this atomic mass is the average mass of all of the isotopes that we find in nature. So for chlorine, for instance, we've got chlorine 35, we've also got chlorine 37. And so we average the abundances of those together to get this overall atomic mass. So how we come up with that decimal number, you guys will need to be able to calculate. So an average mass is found by using all of the isotopes of an element weighted by the relative abundance, or like what percentage they are. This is the element's atomic weight, okay? Atomic weight equals, and this is just an addition sign. So you take the isotopic mass times its fractional natural abundance, and you add it to all the other isotopes. And what will end up happening is that you get a number averaged out that has some sort of decimal in it. So for instance, the mass of any atom compared to carbon, if we have carbon 12, 6 protons and 6 neutrons, but the mass of natural carbon is actually 12, you would think it would be 12, but it's actually 12.012, I believe. And the reason that we have that decimal is because there's also carbon 14 in there. So we're gonna work through one of these calculations using this equation. Let's go to, this worksheet is in your notes. So if you want to find it or reference it at a later date, it'll just be in your notes. So right here, calculating atomic weight. So we're going to do the first one together, and then I'll have you guys do the second one on your own. So for this first one, it says, it's specifically talking about chlorine, and it says naturally occurring chlorine is 75.78% chlorine 35, which actually has an atomic mass, and I'm going to annotate on this, which actually has an atomic mass of 34.969 AMU. So it's not exactly 35, it's 34.969. So whenever they give you the actual in like a decimal form, that's the number you want to use, okay? And then it says, hey, we've also got chlorine 37, which is the remaining 24.22%, which has an atomic mass of, for real, 36.966. So we'll be using that. So when we're solving the natural abundance, it's kind of like if you've ever averaged a weighted grade in a class. So let's say you've got like, I've got 100% on homework, but I have a 20% on tests. Well, the homework's probably not worth the same amount as the tests, right? So in this same situation, the chlorine 35 makes up a bigger percentage than the chlorine 37. So when we're solving this, what we're going to do is the atomic weight. Oh, God, that's horrible. We'll just call it AW, because that is a mess. Okay, so the AW, or the atomic weight, is going to be equal to the mass of chlorine 35 times its fractional, sorry, it's so hard to write in these annotated notes, the fractional percentage, okay, plus the mass of chlorine 37 times its fractional percentage, okay? So because we only have 2 sets of isotopes here, there's only 2 things that we're going to add together. So we take the mass of chlorine 35 times its fractional percentage plus the mass of chlorine 37 times its fractional percentage. I'm going to draw over right over here. So the mass of chlorine 35, again, the mass of chlorine 35 is 35, but if it gives you the more specified number, use the more specified number. So we're going to take 34.969 AMU, and we're going to multiply it by whatever its percentage is. So this is, specifically its fractional percentage. So this is 75.78. We need to divide this thing by 100 to get it out of percentage, or we need to move the decimal over 1, 2, okay? So we're gonna multiply this by 0.7578. So we take our 34.969 and multiply it by 0.7578. If you multiply it by 75.78, it's not gonna work out, okay? You've gotta make sure you divide that fraction or that percentage by 100. Then we're going to take this thing and we're going to add it to the second thing. So we have chlorine 37, but remember, use this. So chlorine 37 actually has a mass of 36.966, and we're going to multiply that by its relative percentage. Move the decimal over 1, 2 spots, or divide it by 100, either or. We'll multiply that by 0.242. Okay, so you solve for what's in the parentheses first, and then you're going to add those 2 things together. So for this top number, I got 26.49951. The bottom one, 36.9. This bottom number ended up being 8.9531. So I will add those two things together. And I end up getting 35.45 AMU, which, if we look at the periodic chart, coincides with what the mass of chlorine is. Okay. So I want you all to do the same thing here, but I want you to do it with silicon. Okay. So go ahead and work through silicon. The difference with silicon, it's a little bit more work because you have 3 isotopes. So you have to do this additional thing 3 times. So you guys have about 4 minutes to chip away at that, and then we'll go over it together. And if you have questions while you're working on it, feel free to ask.
You're on mute.
Thank you. Yeah, I would use the percentages as the limiting number for significant figures with that. So because we've got, when we multiply these out, this has 2 sig figs, which means you'll go out to, this point here and this point here. And then when you add those together, you go with 2 decimal places. So yeah, I would use that as your limiting factor. My husband told me that the phrase of 2020, like there's always like a yearly phrase or whatever, and the phrase of 2020 is "you're on mute." We have to remember 2020 by. All right. So because this is like such a mess, the answers are for all of these notes are in Moodle. So I'm going to pull that up because I can't do the annotation one. It's not working for me. Okay. So all right. So again, we talked about this stuff up here in the beginning. Here are the example problems that we were looking at. So you take your mass of the first isotope. So the first isotope is silicon-28, but it has an actual mass of 27.9796. So that's the number you're going to use. And you multiply it by a really large percentage, right? Most of it is going to be the silicon-28. So we move the decimal over 2 places. That's to get it out of percentage and into decimal form. So it's multiplied by 0.9223, as opposed to 92.23. You won't get the right answer. Then we add that to our next component here, which is silicon-29, which actually has a mass of 28.97649. We multiply that by a very small amount, just 4.68%. When I move the decimal over 2, or I divide this by 100, my new number becomes 0.0468, okay? So again, don't plug the percentage in with this number, divide each of your percentages by 100. That's just the system you got to follow. And then we're going to add that to our final section here, which is our isotope, which is silicon-30, which has a mass of 29.97377 actually, and we are going to multiply that by the 3.09, but we move the decimal over 1 and 2, okay? When we plug this in, we should end up with 28.08541, which would match the periodic chart. I would say round this to 2 decimals. Well, 28 point, let's see. If we multiply these together, 4 sig figs, 3 sig figs, and so probably 1 decimal, so 28.1 would end up being your answer. If for some reason you did 28.09, that's fine. That's going to be close enough. All right. Sig figs, my care for sig figs decreases as the semester goes on. Okay. So, and now I don't want you to give me like a huge number, but with some of these problems that, you know, the sig fig isn't the focus point, I'm not going to be quite as anal. Okay, questions on on calculating this. It's always that same system, all right? You take the mass, multiply it by its decimal percentage, add it to the number of isotopes you have. If you had 14 isotopes, that would be a really crappy problem to do. You'd have to do this 14 times. You're probably not going to get 14 isotopes. It's probably going to top off at 2, 3, 4, something like that, okay? So, so hopefully on the slide, this thing here makes a little bit more sense now when it has that addition thing times isotopic mass times your fractional natural abundance. That makes a little bit more sense. So atomic weight measurements, just FYI, can be measured using a mass spectrometer. In this case, we've got naturally occurring chlorine, and we can see that there's a larger signal intensity for the chlorine-35 than there is for the chlorine-37. Why? Because we have more of the chlorine-35 than we do 37 in existence. All right, so the beloved periodic table. So again, you're going to want to get one of these printed out or have your textbook accessible so that you can be referencing your periodic chart regularly, because we just use it all the time in chemistry. So let's look at some of the different organizations here on the periodic chart. And every periodic chart is going to look a little bit different, like depending on the author of it. They kind of put in what they find important, what they don't find important. So one thing I want you to look at is, or think about, is there being like a zigzag line. And so the zigzag line will actually start underneath hydrogen. It comes over here, it drops next to boron, and it crisscrosses its way all the way down. Usually your periodic chart will have that highlighted in some way, or there'll be a bold line. If you've got a periodic chart in front of you, I want you to like color that in or fill that in. What that does, and I believe your lab manual should have a periodic chart in it somewhere. I don't see one in there. That's so weird. They usually always give a periodic chart in all the lab books for this one.
It should be the very last page.
Very lab, yeah. I think I'm missing a page in my lab book for you guys. That's, oh, hello. Is that you guys down there? Oh, there it is. There it is, buried down in the bottom of my storage bin. It got smushed. Okay, so the last page, yes, does have a periodic chart. So if you want, you can pull that bad boy out, because this is going to be your new best friend. Okay. So this guy already has the zigzag line put into it. But what that zigzag or that stair step line is doing is it's dividing what we call metals from non-metals. Okay, so everything on this side of the zigzag line, all this yellow stuff, even the lanthanides that get inserted here, all these guys are metals. It's the last page. It's the last page. So we've got all the metals over here. And then if you go to the right and or up of the zigzag line, those are all your non-metals. So hydrogen, carbon, nitrogen, oxygen, all the noble gases, these are all non-metals. Now there are a couple things along the zigzag line that are blue. These things we call metalloids, meaning that they sort of have a mixture of properties. Some of their properties are like metals, some of their properties are like non-metals. When another way we can sort of organize the periodic chart, and what you'll notice is like most of the stuff on the periodic chart is metal, okay? So we have a lot of metals, and metals tend to have very consistent properties. Non-metals tend to vary a lot more. So metals in general are solid at room temperature, except for one material that we're gonna have on there, which is mercury. Other than that, the stuff is pretty solid. Over here, we can have things that are solid, liquid, or gas. So lots of varying qualities. These things tend to be shiny. They tend to be ductile. They're easy to pull into wires, what you would think of as a metal quality. They conduct electricity. All these things don't do that. They have a variety of properties. When looking at the rows horizontally, we call those periods. Okay, so period 1 contains hydrogen and helium. Period 2 is a little bit more. We've got lithium, beryllium, all the way to boron through neon. When we get to period 4, we have what's known as our alkali and alkaline earth metals, and then we have transition metals in the middle here. And then we've got our main groups over here. So vertically, we've got a series of groups. The ones you want to know, this over here, group 1, these are the alkali metals. Okay. Group 2 here, these are the alkaline earth metals. These are the transition metals, just this chunk here in the middle. There we go. Over here at the end, this group here is known as the noble gases. They're all gases, and they're noble because they're non-reactive. So So they don't really like to combine with things. You can on occasion get them to form a molecule with stuff, but usually they kind of like to be by themselves. And then this row here, row 7, we call these the halogens. Okay. These guys have names as well, but really you'll hear me just throw around things like noble gases, halogens, alkali metals. All right, so if we look at one of these boxes on the periodic chart, because each of these boxes is representing an individual element. And you'll see that they're ordered in a number, 1, 2, 3, 4, 5, 6. They continue like you're reading a book. The numbers continue upward all the way up to, you know, somewhere around 118. It depends again on the periodic chart. You have some have more, some have less. So what is this number? The number is the atomic number. And if you remember, atomic number is the number of protons. Okay, so the whole number that you see is letting you know how many protons you have. So if I go back here and I say, hey, let's find silicon. Over here is silicon. Silicon is number 14. So every atom of silicon better have 14 protons. Let's say it didn't have 14 protons. Let's say it had 15 protons. Then it would not be silicon, it would be phosphorus. All right. We have the symbol, the atomic symbol, which sometimes correlates, sometimes doesn't. Okay, so in this case we have K, and K represents potassium. So you do need to know that sometimes they are not exactly the same. It's because they're, K is based off of its Latin root name. And then this periodic chart here doesn't have it, but your periodic chart here does have it. It has all the atomic masses or atomic weights. And those are the decimal numbers at the bottom of each box. That lets you know the average mass if we were to take all the isotopes into account. So for instance, here we've got potassium has an atomic mass of 39.0983. So on average, potassium has a mass of 39, but there's an occasion where the mass will be a little bit greater. That's why it's averaging out to that 0.0983. So the rows are called periods, the columns are called groups. It is important to note that elements in the same group, that's why we give them a name, like we call these the alkali metals, and these the alkaline earth metals, and these the noble gases. Things that fall within the same group have similar chemical properties, okay? So lithium is much more similar to rubidium than it is to beryllium. Even though it's right next to beryllium, this is in a different column or a different group. So these have differing properties. But this guy here, lithium and rubidium, they're kind of far away from each other, but they're in the same vertical group, which means that these guys all have similar properties. That is true for all of our main groups here, these guys, and the guys over there. And so what's happening with the two bottom rows? Okay, so the two bottom rows are known as the lantholides. These guys are not included in the main group here, or these central guys here. These transition metals have like more varying properties. They're not predictable. So our predictable groups are going to be group 1, group 2. We call this group 3, 4, 5, 6, 7, and 8. So think of there as being 8 main groups. Then we've got the transition metals that kind of do weird things, and we'll talk about that a little later. And then we also have the lantholides here. Now, if you look on this periodic chart, it jumps from 56 to 71. The reason that it jumps is because we actually have some more elements that need to get plugged into there. So if I was to sort of take this periodic chart and spread it out, split it open, so let's say we were to take this side to go this way and this side to go this way, I could take this whole thing here and we would just whoop, insert it right in there. Again, how that's distributed is different for different charts. If you look at your chart from the back of your lab manual, it splits it up between like 56 and 72, so it starts at 57. 58 is where the asterisk drops you down. Okay. Do we know why the number of protons determines the element? Because that is what gives it its chemical properties as far as defining it by its element. So if you change the number of protons, you will change fundamentally properties that it has. If, for instance, hydrogen, we have 1 proton. If I was to stick another proton in there, it would no longer have the properties of hydrogen. It would now have the properties of helium, just the way it goes. If I change the number of neutrons, it doesn't change the basic properties of the element. It just makes it heavier, or if we took neutrons away, makes it lighter, okay? If we change the number of electrons, we don't change its mass, we don't change what it is, but we do change its charge. We'll talk about that a little later. So when looking at periodicity, what happens is that we have sort of this repeating pattern of properties. When we line all of the elements up in a row, we find that 1, 2, 3, 4, and then there's sort of a gap, and then we get 9, 10, 11, 12, and then a gap, and then 17, 18, 19, 20. And each of these is having similar properties. So the 2, the 10, and the 18 are these non-reactive gases. 3, 11, and 19 are all soft reactive metals. And so Mendeleev, the gentleman who actually came up with the periodic chart, he, they say that he was like on a train, Trans-Siberian or something, and he had all of these elements on a deck of cards, and he was trying to play around with their ordering and how to set them up. And so what he found was that there was this repetitive quality to the elements. So he decided, well, why don't I just take this group here, and where they repeat, I'm gonna just stick it underneath there. I'm gonna sort of truncate it and create a repeated pattern. So that's why the periodic chart is set up like this. It's why we stop at neon and sodium is starting on the next column, because sodium has properties like lithium. So we don't have one long chain. So it makes it really useful. So again, here are the names of the different groups. So we've got the alkali metals, that's the 1A. We've got the alkaline earth metals, 6A, chalcogens. We don't use that a whole lot, but halogens, which is 7A, we definitely use, and then noble gases, we say a lot. So know those. So if I was to ask you, looking at your periodic chart, hey, what is chlorine? You could say, or what group is chlorine? And you could say, oh, chlorine is a halogen. Or what is krypton? Krypton is a noble gas. Or what is sodium? Sodium is an alkali metal. So when talking about metals, so metals will always be on the left side of the periodic chart, or the left sort of down zigzag. Don't include hydrogen with your metals. Hydrogen is definitely not a metal. There are some things that are consistent with metals. They tend to be shiny or have a shiny luster. They like to conduct heat and electricity, just like you would use a metal to conduct electricity versus like fluorine or chlorine. And they are solid except for mercury. Non-metals on the upper right-hand part of the periodic chart, which also includes hydrogen. They can be solid like carbon, liquid like bromine, or gas like neon at room temperature. So they have a much wider variety of properties. Some of them can have sort of metallic-like qualities. Some of them are powderous, some of them are yellow. Some of them are, depending on what phase they're in, they can be red or purple. So lots of different colors and variety happening here. And then we've got our step ladder and those things. are our metalloids. So these guys are actually really useful metals, or metalloids. They're really useful because they have properties of a metal, but they behave in a non-metal way as well. So things like silicon, we put in a lot of electronics because we can get both of these properties. All right, so let's see, molecular compounds. So I want you to spend just 2 minutes here looking over your periodic chart and getting comfortable with where some metals are and where some non-metals are. And if you have any questions whilst looking over the periodic chart, or like, what is this or what is that, please ask me, and then we'll move on. But I want to give you just a minute or two. I don't want to assume anybody's like fully knowledgeable of the periodic chart. So let me know if you need help with that. Okay, great. So you definitely want to be able on your periodic chart to be able to identify where your metals, where your non-metals are, because that will help us later with nomenclature and how we name these things. So chemical formulas, H2 is an example of a chemical formula, H2O is an example, C2H4, there's a bunch of different chemical formulas, but in each chemical formula, the subscript to the right of the symbol of your element tells you how many numbers of that atom are in that element you need. So it's pretty much your recipe for whatever the material is. So if I want to make hydrogen peroxide, I need to have 2 hydrogens and I need to combine it with 2 oxygens. If I only had 1 oxygen and 2 hydrogens, it would no longer be hydrogen peroxide, it would be water. It would have a different set of properties. So you'll always see the symbol written, followed by a subscript number, and then other symbols. If you don't see a number, you can just assume that you have one of them. I wouldn't write H2O, I wouldn't write, I wouldn't write the O if I didn't have at least one of them. So we don't say H2O1, we call it H2O. So when we're talking about types of compounds, there's 2 types of compounds. One is a molecular compound and then the other is an ionic compound. When we're dealing with molecular compounds are composed of molecules, so they're like individual packets like CO2, and they almost always contain nonmetals. Okay, so if you have 2 things from the right side of the periodic chart, we're gonna say that's a molecular compound. So H2O, that's, yes, the H is sitting on the left side of your periodic chart, but remember the zigzag, it's included with the nonmetal. So this is a nonmetal and this is a nonmetal. We would say that this is molecular. Actually, all of these are examples of molecular compounds, 2 nonmetals in some combination together. We do need to talk about diatomic molecules, and you do need to know these. Okay, so diatomic molecules are molecules that don't like to exist by themselves in nature. So for instance, hydrogen, 1 hydrogen atom by himself is not very stable. Okay, so we've got a little hydrogen. he doesn't like to be by himself. So what he likes to do is actually pair up with another hydrogen atom. So if we have a container of hydrogen, the hydrogens are going to stick to each other in these pairings, or we'll have this thing called H2. All right, so hydrogen is H2, nitrogen is N2, oxygen is O2, fluorine is F2, chlorine is Cl2, bromine is Br2, and iodine is I2. Okay, all of these things like to form diatomic molecules. Diatomic is just a fancy way, right? Di meaning two, atomic meaning atom, two atom molecule. You do need to know these, so figure out a way to memorize them. If you want, you can highlight them on your periodic chart. One way that I use it, have no fear of ice cold beer. Have no fear of ice cold beer, but cold is not carbon, it's chlorine. So it may work for you, it may not. Otherwise, it just kind of creates a really nice zigzag line on your periodic chart. You start with your hydrogen, and then you come over and you will have a diatomic with nitrogen, oxygen, fluorine, and then you drop down to chlorine, bromine, and iodine. It makes like an upside down L, okay? So highlight those or scribble in on those and just remind yourself that those guys are diatomics, meaning if they are by themselves, they're going to stick to one of their buddies. All right, chlorine will always be Cl2 if it's in free form. So when looking at different types of formulas, we have empirical formulas, and then we have what's known as the molecular formula. An empirical formula gives the lowest whole number ratio of atoms to each element in its compound. So an example of an empirical formula would be HO. Okay. A molecular formula gives the exact number of atoms in each element. And if you know the molecular formula of a compound, we can determine its empirical formula. The reverse of that is a little bit trickier. So the molecular, one molecular formula of HO could be H2O2. So both of these things have the same ratio, 1 hydrogen to 1 oxygen. This is 2 hydrogens to 2 oxygens, but it still reduces down to 1 to 1. So the simpler one is the empirical. The more, the multiplier is the molecular. You can think MM, molecular multiplier. So I'm going to give you one, and I want you to tell me what the empirical formula is. I'm going to give you the molecular formula. So we've got C3H9O12. C3H9O12. So I want you to try and write its empirical formula or its lowest whole number ratio formula. Okay, so hopefully looking at this C3H9O12, you're seeing that each of these things is divisible by 3. So we would take, we would go ahead and take each one of these numbers and divide it by 3. So that first one would become just carbon with a 1. We don't need to write the 1. Hydrogen would be H3 and oxygen would be O4. So CH3O4 would be our empirical formula for this molecular formula. Different ways that we can represent molecules. So we can look at the molecular formula, and hopefully with time, you'll be able to look at the molecular formula and start to sort of visualize some of these 3-dimensional shapes. But we've got our molecular formula, then we've got what's known as a structural formula. So in this, we take our atoms and we try to arrange them relative to each other. So in this molecule, carbon is in the center and the 4 hydrogens are connected to the carbon around it. This does not depict what it looks like in three-dimensional shape though. It is not a flat molecule. It actually has like a forward and back direction. So another way is to do a perspective drawing. In this case, we've got carbon with two hydrogens that are parallel. Then we've got a hydrogen that's got a wedge. This is sort of pointing out towards you. And then we've got this dash. The dashes always mean it's pointing back into the page. This one may be a little bit friendlier to see what's going on here. Here's our carbon. There's our carbon. We've got a hydrogen and a hydrogen parallel. Then we've got this carbon coming forward and that carbon going back, making this tetrahedral shape. Sometimes you'll also see these space filling models where they just sort of bloop the atoms together. So talking about ions, so an ion is a charged atom. And we have two different ways that we can think about ions. We can think about them as, or just, we can sort of break this down into cations and anions. So a cation is formed when you lose at least one electron and you form a positively charged ion. So again, a cation is a positively charged ion that has lost at least one electron. Because remember, what is an electron? An electron is a negatively charged thing. So one way that I've taught this in the past is to think about electrons like that negative person in your life. All right, so if you have a lot of electrons or you have a lot of negative people in your life, you become more negative. If you get rid of an electron or you get rid of one of these negative people, you become more positive. Okay, so loss of electrons creates a positive charge. Then there's the opposite of that, because if things are losing electrons, something else has to be gaining electrons. Otherwise, we'd have all these free floating electrons everywhere in the universe. So anions are things that form a negative charge. The way it forms a negative charge is it gains an electron. As far as the periodic chart is concerned, metals tend to form cations. So cations, metals. Anions, non-metals. Okay. So stuff happening on the left of the zigzag will form a positive. Stuff happening on the right of the zigzag will form a negative. One exception, hydrogen. Hydrogen is a non-metal, but it does form a positively charged ion. So one thing you can do on your periodic chart, if you've got it out, is above column 1, right here where hydrogen is, put a +1. Because everything in that column predictably likes to form a +1 charge. So that means hydrogen, lithium, sodium, potassium, rubidium, and cesium all like to give up one electron to form a +1 charge. Over column 2, minus beryllium, because beryllium does sort of weird things. Over column 2, you can put a +2 charge. So magnesium, calcium, strontium, and barium, those guys all like to give up 2 electrons to form a +2 charge. Because remember, if you're giving up 2 electrons, if you're giving up 2 negative people in your life, you should become more positive by a factor of 2. The noble gases don't form ions. So above them, you can put like a 0 with a slash through it or something, or Na, not applicable, because those guys don't like to form a charge. Everything in column 7 here likes to take on 1 electron. If we take on 1 electron, we're going to become a little bit more negative. So put a -1 above column 7. Everything in column 6 here likes to form a -2 charge, or they take 2 electrons on. So put 2- above your oxygen column. And then above nitrogen, you can put a 3-. Sometimes phosphorus also forms a 3-. Sometimes those ones are a little bit trickier. Aluminum is a 3+ charge. And when you're looking at your periodic chart, I want you to go in a zigzag down into the left. okay? So you'll see aluminum is a 3+, then you should see zinc here. Zinc is a 2+ charge, okay? It forms a predictable 2+ charge. And then if you go down one more, we get silver or Ag. That is a 1+ charge. It's so badly written, but put a 1+ there. So as a zigzag, we have 3+, 2+, 1+. Those are predictable charges that you need to know. All these other things, all these other transition metals don't have predictable charges. They do weird things, okay? That's why we call them the transition metals. That's why we don't put them in our main group elements, because they don't have predictable properties. But these three do. So 3, 2, 1. Okay, so some of the common cations, again, a cation, you can see the T makes a, in cation, it makes a plus. So that's a positive ion. It's one way to remember it. Some people like cats, so they think they're positive. So that's why they're positive. I don't really like cats, so that one doesn't work for me. But anion just sounds negative, right? Anti. So some of the different cations that we can see, there's also these things over here where we can have an actual formula that has a positive charge as well, like ammonium. This is a polyatomic ion. We'll talk about that in a minute, but ammonium has a plus charge. Copper, that guy in the middle, our copper one, has a +1 charge. So the transition metals in the middle, these guys here, outside of 3, 2, 1, these guys don't have predictable charges, which means that they can vary in charges. So you have to like let the reader know what the charge is. So that's why they say that this is copper 1. When you see copper 1, it's not saying you have one copper element or atom. It's saying that you're dealing with copper with a +1 charge. We look over here, cobalt 2+. We're dealing with cobalt 2 because it's a 2+ charge. This is copper 2, iron 2, so on and so on. If we go down here, we can see that we have chromium 3+ with a 3+ charge. That means that we're dealing with chromium 3. You have to specify which one you're using. So if I have a formula, I can't just say it's iron oxide. I have to say it's iron 2 oxide, or I have to say it's iron 3 oxide. Because if it's iron 2 oxide, it has a 2+ charge. If it's iron 3, it has a 3+ charge. These two things will behave differently. You don't need to have these memorized because you can always figure out from the formula or from the name which one you're working with, but you do need to know that those relate to each other. Okay, so there's a charge and then there's a Roman numeral that comes after it. Here are some common anions, and we can see that there are also these things called polyatomic ions. So acetate ion, chlorate, perchlorate, nitrate, carbonate, chromate, sulfate, all these things. What is common with everything on this page? They're anions, meaning they all have some capacity of a negative charge, or they're holding on to more electrons. If they have a -1 charge, or just a minus charge, it means they have 1 additional electron. If they have a 2- charge, it means they have 2 additional electrons. Let's see, over here, phosphate is a 3- charge. This thing has 3 additional electrons stuck to it. So all these things here are known as polyatomic ions, which is just a fancy way of saying poly, meaning many or multi, right? So polygamy, multiple wives, polytheist, multiple gods. So poly, multiple atomic atoms. So multi-atom ions, and ions just means that it's charged, right? So you've got a package of atoms, more than one atom, and they have a charge to it. So one example of a polyatomic ion is NH4 plus. So here we've got 1 nitrogen mixed with 4 hydrogens. And when those things come together, they are going to give up 1 electron to form a positive charge. And I'm not going to get into details right now why it likes to give up 1 electron, but when we get into shapes and stuff, it'll make more sense. Another polyatomic ion, this is specifically a polyatomic anion, is sulfate, SO4 2-. Okay. Now, when looking at SO4 2-, I really want you to, start to mentally put maybe like a zigzag between the middle of it so that you're separating the numbers that are below or subscript from numbers that are above or superscript. Subscript numbers below tell you the number of atoms. Superscript above tells you the charge. All right. So in this case, I've got, when looking at this packet, I have a sulfur, I have 4 oxygens, and this whole packet has a 2- charge. So if I did sulfite, which is SO3 2-, looking at this thing, this has how many sulfurs? I've got 1. How many oxygens? I have 3, and that whole thing has a 2- charge. So this guy is just a little bit different than this guy in that this guy has 3, this guy has 4. So there should be a list of polyatomic ions in your textbook. Normally, during a normal semester, I would expect you guys to have a good amount of the polyatomic ions memorized, usually like carbonate, sulfate, phosphate, nitrate. But since we are a semester of new challenges, we will also have new compassion and grace. So you guys don't have to have polyatomics memorized, but you do need to be able to reference them, okay? So have the polyatomic ion, you can print one out. If you type on Google like polyatomic ion sheet, you can print one out and have that with your formula sheet so that you can just reference these things really quickly. All right. So ionic compounds, we talked about molecular compounds being made up of 2 nonmetals, like CO2, for instance, carbon dioxide. Ionic compounds, such as NaCl, are generally formed between 1 metal and a nonmetal. So you have one thing from the left side of the periodic chart and one thing from the right side of the periodic chart. This is a different chemical setup than our molecular compounds. In our molecular compounds, where we have 2 nonmetals, we share electrons, or those have what are known as covalent bonds. In our ionic compounds here, we have a transfer of electrons. So what happens is we have sodium. Sodium has 11 protons and 11 electrons, but he wants to give up 1 electron because he's in column 1, right? He likes to form a +1 charge. Chlorine has 17 protons and 17 electrons. Chlorine likes to take on an electron. It's in column 7 where the halogens are. So what happens is this thing will lose an electron. This thing will take the electron on. So now we've got 2 new ions here. We've got an Na, we've got an Na plus ion, short 1 electron, and we've got a chlorine minus with an additional electron. This has a positive charge and this has a negative charge. What do opposites like to do? Opposites attract, right? So positive and negatives will stick together just like the opposite ends of a magnet. So stick together. So when we're dealing with an ionic compound, one thing has a positive charge, one thing has a negative charge, and they stick together and form this lattice structure. All right, so when we're gonna write a formula for a charged, for 2 charged particles that are ionic, this is how we do it, okay? It's gonna seem sort of weird, but you take just the magnitude of the predictable charge of the first guy and you put it as the subscript of the other guy. Then you take the charge of the other guy and you put it as the subscript of the first guy. So magnesium always forms a 2+ charge. Why does it always form a 2+ charge? Look at what column it is under your periodic chart. It's under the second column and you wrote a 2+. Nitrogen forms a 3- charge. Why? Because you wrote on your periodic chart 3- above your nitrogen, okay? So the 3 gets dropped down to where the magnesium's atomic number is, or how many you have. The 2 gets dropped down to the nitrogen, or you flip-flop. This is the fastest way to find the lowest whole number ratio without having to like mentally think about it. Because if you think about it like here, okay, magnesium has a 2+, nitrogen has a 3-. I know my end molecule has to have a 0 charge, so I need 3 of these to balance out 2 of those, because that'd be 6+ and 6-, blah, 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 blah. Just flip-flop and it'll give you that answer right away. This final thing here, we would call this magnesium nitride. This guy has an overall charge of 0. When you have an ionic compound, your overall charge will be 0. Magnesium has a 2+ charge, right? And we're saying that we have 3 of them, so that's a 6+ charge. Nitrogen has a 3- charge, and we say that we have 2 of them. That's a 6-. 6+ and 6- equals 0. So the flip-flop method for ionics, you can only use this when you're dealing with a metal and a non-metal. Don't use this if you're dealing with 2 non-metals. It doesn't work. So let's try a couple of those flip-flops before we finish up. We've got 1 minute left. We can do it. We can do a couple. Oh, hello, that's my daughter. She got a hold of my computer. Let's clear that out. Okay, so let's say we're gonna combine aluminum and oxygen. Okay. So the way that I'm gonna do this is I'm gonna write the symbol for the metal first, Al, and then I'm gonna write its charge. What is aluminum's charge? What does it like to form? 3+, 3+, okay? Oxygen, what does it like to form? 2-, okay? Why? Because of where it is on the periodic chart. So what we're gonna do is flip-flop these. So this 3 is gonna get dropped down here. This 2 is gonna get dropped down here, and I get Al2O3. That is the correct way to write aluminum oxide. I'll do one more. Let's combine nitrogen. No, let's combine magnesium and oxygen. Okay, so the first thing I'm gonna do when I'm writing a formula for magnesium and oxygen is I'm gonna write the symbol for magnesium, which is Mg. It has a 2+ charge. Oxygen always has a 2- charge. If you don't know how I'm getting those numbers, stay after and ask me. Flip-flop these, it should become Mg2O2, but since these are both 2 and 2, I can reduce them when they're ionic, so it will end up being MgO, 1 magnesium for every oxygen to balance it. Okay, so we'll stop there. We will do more practice with that next time. Don't worry, I feel like we felt a little rushed there, but we will do some more practice. Stay after if you have questions. Get to that nomenclature lab sooner than later so you can start practicing some of this stuff, and we will finish this up on Thursday. Okay, bye guys.